Here in this video, we are solving a problem. Let me read out the problem for you. 1 mole of monoatomic gas. So before going further, we need to know many things about monoatomic gas. What is its degree of freedom, internal energy, how do you measure its CV, and how do you find the value of gamma. So I will keep the problem aside for a while and talk about these parameters, right? Yeah, so let's focus a little on what do you mean by a monoatomic gas. So my first question is, what is a monoatomic gas molecule first of all? Yeah, let's assume this is a lesson on monoatomic gases for a while. Mono means only one. Atomic or molecule means having only one mole or else one atom. So a gas who is having only one atom is called monoatomic. The example is like helium. You say He, you will never say He2. Whereas for hydrogen, you will say H2. That's a diatomic gas. So monoatomic, simple example is like a helium who is having only one molecule. So what is its degree of freedom? Let us try to understand what is the meaning of degree of freedom. Degree of freedom means it's a measure to say in how many ways it is free to move. It can move along x-axis. It can move along y-axis. It can also move along z-axis. So, degree of freedom for a monoatomic gas molecule is 3. See, it is not going to vibrate because it's not having that vibrational transitional energy. It's not going to rotate because there is no other one around which it can rotate. So it has a degree of freedom of only 3. Then you need to know one more thing, that according to law of equipartition energy theorem, each degree of freedom contributes the internal energy of gives the internal energy. So because of this motion, molecules possess translational kinetic energy. That's called internal energy. So each degree of freedom gives an internal energy of half of RT. This is having 3 degrees of freedom. No? That implies for monoatomic, total internal energy is 3 times of half RT. Half RT is the internal energy of each molecule. I mean, each degree of freedom. There are 3 degrees of freedom. Therefore, it has a total internal energy of 3 by 2 RT. So, if you keep that aside just for a minute, I would like to go further to the next point, that what's the definition of that specific heat of a gas at constant volume, defined as amount of heat required to rise unit mole of gas by 1 degree centigrade at constant volume. As we keep the volume constant, change in the volume equal to 0. But we know, as for the first law of thermodynamics, total heat supplied is sum of change in internal energy and external work done by it. So work done can be written like P dV, but being a constant volume, dV equal to 0. So dQ equal to du plus 0. That is equal to du itself. So you can rewrite the definition of CV as 1 by n du by dt. Now I know the value of that du as half RT. That implies you can say half RT where the meaning of that T is a change in temperature itself. So if required, we can even write it like dt also. If you write that and come back to this place, what happens to the value of this? N is already equal to 1. Assume for an ideal gas of 1 mole, du can be written like 3 by 2 r dt, basing on this. By dt is there for Cv. dt cancels. That is 3 by 2 times of r. That's how we get the value of Cv for a monoatomic gas. Just in continuation to this, once if you know Cv, we know Cp minus Cv equal to R. Cp is Cv plus R. But I found Cv as 3 by 2 times of R. One more R is there. 5 by 2 times of R. Cp. So I got Cp. I got Cv. I know gamma as a ratio of specific heat, Cp by Cv. That is 5 by 2 times of R by 3 by 2 times of R. That is equal to 5 by 3. I want to tell you that to solve this problem, having a knowledge up to here is sufficient. This is sufficient. But anyway, I have just continued that discussion and shown the next possible parts of it so that you will be able to use them in your further solving problems wherever it is necessary. So you can consider this part as a, up to this, whatever I have done in this video for these 7 minutes, as a part of a story about monoatomic gas. And if you are not interested in that, you can simply skip that part and go to the problem itself. Now I am ready to go to the problem itself. What is the problem says? Taken from A to another point B along the path ACB. What is that path along the ACB? Is this A to C and B in 2 steps. It was gone from A to ACB. Then temperature at A is given as T0. Calculate the heat absorbed in this process. So let's go to the problem now and try understand what he want. He want to calculate total heat absorbed to move from A to B via C. For the first law of the, as per the first law of thermodynamics, in the place of dq, I can write du plus dw. So if you have to calculate the value of du, you have to calculate the value of dw, and then substitute all of them, right? So what is du? Let's calculate du first. As n into Cv dt. N equal to 1. Cv equal to, you know the value already. 3 by 2 times of R. But what is dt? We don't know. So what we want to calculate is, during A to B, what is dt we have to calculate. What is change in temperature when the particle moves from A to B? How can I calculate? Being an ideal gas, we can apply ideal gas equation, that PV by T equal to constant. So PA VA by TA equal to PB VB by TB. PA is given for you as P0, VA is given as V0, TA is given in the problem as T0. PB is given to you as 2P0, VB is given to you as V0. By TB we have to calculate. This P0s, V0s can be cancelled. So TB equal to 2 and 2. 4 times of T0. It implies a dt equal to TB minus TA. That is 4 T0 minus T0. that equal to 3 naught. Now I got the value of dt. I can substitute that and get a change in internal energy. du equal to 3 by 2 r and then 3t naught. So the value is 3 and 3 9 RT naught by 2. That's the value of du. You got the value of du. Now to continue the problem, I need to know the value of dw. So my next thing that what I have to calculate is what is dw. So my next thing what I have to calculate is dw during A to B. It is happened in two steps, A to C and then C to B. So I can say work done during AC plus work done during CB. This part and this part. Work done during AC, work done during CB. But work done during AC can be written as a formula PdV. Why? During A and C, P is constant, P naught. dV is change in volume. It has moved from V naught to 2V naught. So 2V naught minus V naught. So it is P naught V naught. Now work done during CB is PdV, of course. Work done during CB. P is changed. Of course, I can say whatever. But I would like to say it is 0 as dV change in the volume during CB is, it is 2V naught here. Here also it is equal to same 2V naught. So there is no change in volume. So work won't be done when there is no change in volume. That implies total work done is work done during AC as P naught V naught. Work done during CB as 0 because the volume is a constant there. So the total work done is P naught V naught. Now you know dW. You know the value of du. So let us add both of them so that I can get dq. That implies we can write dq as first law of thermodynamics du plus dw. In the place of du, 9 by 2 RT naught. But in the place of PV, I can write this PV also as RT naught because n equal to 1. Because PV equal to nRT for an ideal gas. As this term is in RT naught, I will write this also in RT naught. So it will become 11 by 2 RT naught. So we need to supply a energy of 11 by 2 times of RT naught, where T naught is the temperature at A, so that it will move from A to B. That's how you have to solve the problem. So I want you to understand very carefully that we have discussed a lot about monoatomic gas in the first part of this discussion. And this is a very important discussion. We can do the same for diatomic and polyatomic gases and find the values of gamma in any of these cases. That's how we have to solve the problem, right? Thank you.